Hey there, welcome to this video on Gradient Ascent. I'm going to show you how to create this contour plot and then how to go about calculating the gradient ascent solution over this function. In gradient ascent, we're trying to find the maximum value, that local maxima, over a given domain from a given function. If you're looking for the minima value, that's going to be gradient descent, and I have another video on that on my channel. Let's start by looking at the gradient ascent equations. Here are the gradient descent equations for 2D and 3D. The only difference for gradient ascent is that we add in pluses where there were minuses. Here in the 3D case, we have some function z, which is a function of x and y, and now we have x and y coordinates that we're working with. Here I plus 1 indicates the next value, and I indicates the current value. We're always calculating the next value from the current value, and we add in a gamma weighted term, or learning rate, times the gradient of this function. The gradient of that function can be reduced to two partial derivatives with respect to either variable x and y. And if we split this up, we can solve for x and y independently, and we can use the partial derivatives independently as well. Once we solve for these, and we'll get these partial derivatives from MATLAB, we'll get new x and y values. We can plug those into the initial function to get our new z value. And then we do this over and over until we get our solution to converge. The algorithm is fairly straightforward. Follow along this video, and you can get this code on my GitHub. Check the link in the description. The first thing we need to do is define our main function that we'll be doing gradient ascent upon, which I have as a negative quarter x squared minus y squared. Both an anonymous function, so we can use this throughout the code, and symbolically here. If you want to do the symbolic approach, you need the symbolic math toolbox in your MATLAB installation. I want to create a visualization, that contour plot, that surface plot that we've been seeing earlier, and I'm defining that with these commands here. That gives us this colorful base plot without the red dots. Then we come into the algorithm, and we need to get these partial derivatives solved for. You can do this analytically by hand, or if you want, MATLAB has some functions that may be able to help. The diff function will calculate the partial derivative of fs with respect to xs and ys. And I'm saving these as a symbolic expression here. Note I defined fs and xs right here. I want to be able to use these symbolic expressions as anonymous functions, so I can plug in a value and get an output. And you can convert them using the MATLAB function command. Saved to gradx and grady now as anonymous functions. We need to start with some initial conditions, initial x and initial y, and we can solve for our initial z using the anonymous function we defined at the start of the script. These can be random values here, your choice. But I'm saving these in a matrix called points, and each row will be an instance of x, y, and z. This is our learning rate, called gamma in the equations. I've renamed it alpha here. Usually start with this being a small value, and we'll look at what happens when we change this value in a little bit. When it comes to the algorithm, we're going to keep doing a while loop until the distance between two consecutive points becomes very small. Essentially, we want to keep sampling new points until the distance between these becomes super small. If we're moving far, keep going. If we're moving only a short distance, stop. And I've defined an error in the x and the y to do so. We need to calculate the next x, y, and z pairs of points by using the equations that we saw in the PowerPoint slide. Here is the current point plus that alpha term times the gradient partial derivative here in both x and y. And I'm using those grad x and grad y terms that I defined up here. You could also hard code these values in instead of using the MATLAB symbolic toolbox. You just simply need to calculate what the partial derivatives are of your initial function. Then we have to update that difference between the consecutive points, which I'm doing right here by taking the difference between the new point and the old point. And then I'm keeping this counter I. This is just a handy thing to have so you know how many loops have been done. And in the instance where a solution doesn't converge, I want to be able to break out of this loop after 200 iterations. Last but not least, I'm making a scatter plot of the red points, shown here, and I'm providing an output so we know how many iterations it took, 61 in this case, and what the final point is, which is ultimately our solution. Let's take a look at changing the learning rate to 0.5. We converge in 19 iterations, and you'll see that we no longer have those intermittent points going to the peak. It simply jumps straight there and then goes faster to the solution. This can be positive because you're looking to converge faster. It's less computational time, but be careful as you increase this. You might get some undesirable behavior. In this case, we overshoot from our initial condition over the half pipe and then back, and we ultimately get to the solution in 13 iterations. But if we increase this to 1, you'll see that we keep half piping, completely overshoot, and then continue to do that throughout the course of the algorithm. In this case, we never actually converged to the correct solution, and the difference is always very large between consecutive points. Hence, our while loop ended up doing 200 iterations, and we only broke out because we added this if statement here. That's it for Gradient Ascent. If you're curious about Gradient Descent, check the description. I have a link to that video. I hope you enjoyed this, and please add any comments below in the comment section. Thanks for watching, and have a great day.